I just want to review for a minute the properties we have that we use to solve equations. First of all, the addition property. If we say if A is equal to B, then A plus C is equal to B plus C, and the other way around. If this is true, this is true, and if this is true, this is true. That's why I have the double-sided implication right here. Now our multiplication property, same idea. If A is equal to B, then A times C is equal to B times C, as long as C isn't 0. And if A times C is equal to B times C, then A is equal to B. So A equal B if and only if A times C equal B times C, as long as C isn't equal to 0. So both of these properties that we've used for a while go in both directions. If this side is true, then this side is true, and the other way around. Now our property for solving equations that have square roots in them, the squaring property of equality, says if A is equal to B, then A squared is equal to B squared, but not the other way around. Because just because A squared is equal to B squared doesn't mean that A is equal to B. For instance, if A squared equal B squared could look like this. Negative 3 squared is equal to 3 squared. Well, that doesn't mean that negative 3 is equal to 3. So this implication only goes in one direction. So what does that mean for you? Well, if you solve equations and you use this property, which you can whenever you want, it simply means that you have to check your solutions in the original equation that you had before you applied this property to be sure that you haven't ended up with something that looks like this and unknowingly said that negative 3 is equal to 3. So what I want to do is go to the next board and solve an equation using this property and show you what I mean. So let's go to the next board. We want to solve the equation square root x plus 15 is equal to x plus 3. Okay, we're going to use our squaring property here to square both sides so I can get rid of the square root right here and solve the equation. Then I just want to remember when I do that, I need to check all my solutions back in the original equation. That's this one. So I'm going to write my equation down again. Square root of x plus 15 equal to x plus 3. And we're looking for all the numbers x that make this true. I'm going to square this side, and I'm going to square this side. So that's my squaring property of equality, and so I've done that. Now, when I square this square root that's over this whole thing, I end up with just x plus 15. On this side, I have to square this binomial x plus 3, and so I get x squared plus 6x plus 9. Now, I have a quadratic equation. I want to put it in standard form, so I'll add negative 15 to each side, negative 15 to each side, and negative x to each side. So on the left side here, I get 0 is equal to x squared, 6x, and then I'm going to subtract 6x, so plus 5x. And then 9 plus a negative 15 that I add to each side, I end up with negative 6. Is equal to 0, so I want to factor this now. So I'll say 0 is equal to, I'm looking for two numbers to multiply here and here to give me x squared, x and x. Two numbers to multiply and get negative 6 and add and get 5. Those would be positive 6 and negative 1. Set these factors equal to 0, so x plus 6 is equal to 0, or x minus 1 is equal to 0. In either case, I get a solution to my equation, x equal negative 6, or x equal positive 1. So here are my two possible solutions to my original equation right here, but because I applied the squaring property right here, I need to check each solution. So let's do that. Let's check this solution. I'll take x equal negative 6 and put it back into this equation. I get square root of, negative 6 plus 15 is equal to negative 6 plus 3. Negative 6 plus 15, that's 9. So square root of 9 equal negative 3. I end up with square root of 9, which is 3, equal negative 3. That's not going to work, right? That's a false statement. So because this is a false statement right here, that means that x equal negative 6 is not a solution to my original equation. And that's what happens when we use that squaring property. Sometimes we'll square both sides and we'll end up with a false statement in just the right form that it makes this true. If I have 3 and negative 3 here, their squares are equal, but that doesn't mean that those two things that we started with are equal. Let's just check x equal 1 to end this here. 1 plus 15 under that square root. 1 plus 3 on the right side. 1 plus 15 is 16. Square root 16 equal, I have a 4 over there, and so the positive square root of 16 is 4, equal 4. That's a true statement, so that true statement means that this actually is a solution. So here I've solved the quadratic equation. I get two possible solutions right here. This one doesn't work because it turns this thing into opposites that aren't equal to each other, but whose squares are equal to each other, and this right here, which is true, meaning that x equal 1 is that solution. So what does this mean? It just simply means you can square both sides of an equation anytime you find that it's convenient, like when you want to get rid of the square root right here. If you do so, you just have to check every solution that you have back in your original equation. Okay, let's go back to our original board for just a second. So you can see actually in that case, in solving that equation, we actually ended up with a statement that looked like this, but we didn't know it because we have an equation that involves x and we don't know what x is yet. So we solved the equation using this property, and what happens is we end up with a statement like this. We end up with a solution that gives us a statement like this, and we don't want to say that this is true. Negative 3 is equal to 3. So that implication doesn't go in this direction right here, and you can see that's why it's a good idea to check all your solutions. Now, it turns out that this squaring property can be a fourth power property, sixth power, eighth power. Anytime we raise an equation, both sides of an equation, to an even numbered power, we always have to check our solutions. Now, if we were to say a is equal to b, then a cubed equal b cubed, those kind of implications go in both directions because you'll never get a situation like this with odd-numbered exponents. Odd-numbered exponents keep negative numbers negative and positive numbers positive. So we can extend this property to other exponents as well. Simply what you have to remember is if you raise both sides of an equation to an even-numbered power, you always have to check your solutions back in the original equation that you had before you applied this property.